Okay, so let's do our first related rate problem. Suppose oil spills from a ruptured tanker and spreads in a circular pattern. If the radius of the oil spill increases at a constant rate of 4 feet per second, find the rate at which the area of the spill is changing when the radius is 30 feet. Okay, so that sounds like a mouthful, but let's just go ahead and draw a picture, identify our givens, our unknowns, and then try to relate our variables, just like we would do for any word problem. So I'm going to draw a diagram first. What's going on? We have an oil spill, and we are assuming that it is increasing in a circular pattern. So at one moment in time, the oil spill looks like this, where here's my radius, and then a little bit later, there's a larger circle of oil on the water. There's my radius. A little bit later, there's a larger circle still. What have they given me? They've given me the rate at which the radius changes with respect to time. They did that right here. They said that the radius of the spill increases at a constant rate of 4 feet per second. So say right here we've got my radius is 1 foot, and then another second later my radius will be 4 feet, and another second later we've got another 4 feet added on to that, 8 feet. So my given is that my radius increases at a constant rate of 4 feet every 1 second. So if I let r be my radius, what they've given me is dr dt, or r prime if you prefer. Because it's increasing, it's positive 4 feet every 1 second. You can write r prime is 4 if you prefer. What have they asked me to find? They've asked me to find the rate at which the area of the spill is changing at a particular moment in time when the radius is 30 feet. When the radius is 30 feet. So I'm not even thinking about how to solve the problem yet. I'm just laying out what they've given me, what they're asking me to find. So my unknowns, we're asked to find the rate at which the area is changing with respect to time at a particular moment in time when my radius is 30 feet. If A is my area, what they've asked me to find is the rate at which area changes with respect to time, or if you prefer, A prime, at a particular moment in time when r is 30, when the radius is 30 feet. Now, one thing to keep in mind is because my radius keeps increasing, so does my area. So we're going to expect dA dt, or A prime, to be positive. Let's just write that note. Since the area is increasing with respect to time over time, dA dt, that's an A, or A prime if you prefer, must be positive. So that's what they're asking me to find, that derivative, that rate of change. they gave me a particular rate of change and they're asking me to find another rate of change. This rate of the given rate of change has to do with the radius. The unknown rate of change has to do with the area. So I want to ask myself, how is the area of this oil spill related to the radius of this oil spill? Well, we know, since it's a circular pattern, the area of a circle is pi r squared, not 2 pi r. You live in an apartment or a house with square feet, right? The area of a circle is pi r squared. So let's go ahead and relate the variables. And in this case, what are the variables? R being the radius and A being the area of our oil spill. We know that the area is equal to pi times my radius squared. Now that doesn't have a derivative involved with it, so the next step is for us to take the derivative of both sides with respect to time, with respect to t, just like we did in our warm-up, right? Taking the derivative of both sides with respect to t, with respect to time. Every time you take the derivative of a function that is changing with respect to time, you're going to have to hit it with another derivative using your chain rule, right? So like what I'm saying here, all the pinks are going to come into play. Okay. Oh my goodness, I'm writing so big. So now we're going to differentiate both sides with respect to time. Okay? The derivative of A is 1, but then chain rule times dA dt, the rate at which A changes with respect to time, or A prime if you prefer. Here I have a constant, pi is just a number, about 3.14, a constant multiple. If I were to take the derivative of r squared, I'd get 2r, but wait a second, r changes with respect to time. We're going to have to then use chain rule and multiply by dr dt, or r prime if you prefer. Pi times 2 times r to the power of 1, chain rule, need a new color, times dr dt. Okay, now we need to go ahead and plug in what we know and solve for dA dt, or A prime if you prefer. That's what we've been asked to find. What's the rate at which the area changes with respect to time? At a particular moment in time, what moment in time? When the radius is 30 feet. Maybe we'll even get a new color on that. Excuse me, I apologize. When the radius is 30 feet. They gave me dr dt, or r prime, as positive 4 feet per second. The radius is increasing at a constant rate of 4 feet per second. Go ahead and plug that in. Okay, and now we'll just do this algebra. dA dt, or if you prefer, A prime, the rate at which the area changes with respect to time, is equal to pi times 2 times 30. And if you want to include the units, you can. 30 feet times 4 feet per second. If we want to include those units. Multiplying straight across, we get our final result. A prime is equal to 2 times 30 is 60, times 4 is 240, times pi is 240 pi. Feet times feet, that's square feet per second. And that's good that those units work out here. My area units are square feet per time unit per second. And we are all done. I do think we should write it in a complete sentence. Let's do that. The area of the oil spill this is a positive rate of change. The area of the oil spill is increasing at a rate of 240 pi square feet per second. If you want to write per 1 second, you're more than welcome to. And when does this happen? At a particular moment in time when the radius of our oil spill is 30 feet. Excellent. So let's now think about what the steps were to approach this problem, and then I want to share some common mistakes with you before we do some more examples. Okay, so what were the steps that we used? We first want to read the problem carefully a couple of times and take some pressure off ourselves to instantly know what the answer is or how to approach it. Just familiarize yourself with the problem. Often drawing, not always, but often drawing a diagram with related rate problems is helpful because the way in which variables are related to each other is often geometric. Then you want to identify what they've given you. What quantities did they give you? What rates of change did they give you? And then identify the unknowns. The unknown in a related rate problem will always be a rate of change. It'll always be a derivative. Then you want to relate your variables. Set up an equation, right? So we set up pi r squared. The radius and the area of the circle are related in that way. And then differentiated both sides with respect to time. Differentiate both sides with respect to time. And lastly, you want to substitute the given information and solve for that unknown rate. So we substituted in 30 for r and 4 for r prime, dr dt, so that we could solve for dA dt, a prime, if you prefer that notation. Some common mistakes are to go ahead and substitute in numbers too soon. If something is truly constant, if it's not changing over time, then it's perfectly fine to just treat that as a constant, treat it as a number. But notice here in this example, yeah, they told me R was 30, but my radius of this oil spill is changing over time. There's only one moment in time when the radius is 30 feet. So you do not want to substitute in that 30 for R too soon. Let's see why that would be a problem for us. If we said that the area is pi times the radius squared, and we're really excited, we're jumping the gun here, and we're saying, oh my goodness, I know what R is. I saw an R up in the writing. They said R was 30, so let me go plug that in. Oh, A is 900 pi. Wait a second here. That's just a constant. I'm acting like the the area is always 900 in pi square feet. If you then go ahead and differentiate with respect to time, what do we have? Oh, we have the derivative of a constant. This is just a number. Oh my goodness. Oops, I didn't write prime. A prime or dA dt is 0. That's not what we're asked to find here. So it's fine to make substitutions for things that truly are constant, things that truly don't change over time. Things that do change with respect to time, you want to wait until the very, very last step, until you've actually taken a derivative, and then you're plugging in the knowns to solve this problem. The second really common mistake is to not notice if a rate of change that they gave you was positive or negative. So a totally different example, if you're given that a car is driving towards an intersection at a rate of 30 miles per 1 hour, and if I let X be the distance that that car is from the intersection, well, as I'm driving towards the intersection, the distance that I am from the intersection is decreasing with respect to time. So dx dt, or x prime, the rate at which x, the distance I am from the intersection, changes over time with respect to time, must be negative. The mistake is to just see a 30 and then write a 30, right? So here's my silly little car. And it's driving towards my intersection. X is the distance that I am from the intersection. Over time, X is getting smaller and smaller, right? Since that distance is decreasing, its rate of change must be negative. Oops, I want them red. Oop. So the mistake is to just see a 30 and use a positive 30. And that's it.